All right, welcome to Quarantined Math Analysis Day 4 with special guest star Mint the Cat. What we're going to work on today is a derivatives problem, and he wants to jump, but we're going to be talking about derivatives. We are going to be working out one of those problems where we are trying to find the slope of a point on a line. I know that derivative stuff is very difficult, very confusing whenever you first start working with it. But like a lot of things, the easiest way to get through something is by seeing it in action. Not just having explained to you, but seeing some hands-on examples, seeing it in many different ways. So that's what we're going to try to do today. We're going to do that hands-on example. I think it will make sense to several of you guys. I think it will help help the idea kind of click into place in what it is and what we're doing. But even if you're still having difficulty with it, I want you to know that's okay. This is very much a learning process. It's very much something that may take a little while for some people to really grasp a hold of. But do your best, try to keep up as best as possible, and ask me any questions if you have any at all. All right, today we are going to work on finding the derivative, or the slope of a single point of an equation. So the function we are going to be working with today is this one right here. The function of x is x squared plus 5. Now if we were to graph that, it looks right about like this. This is a parabola. That's the origin right down at the very base of the screen, so it's just a little bit above that origin, but that is the parabola that we would see when we graph that function right there. Now we said that if we wanted to find the slope of any point on this parabola, then what we would do is we would have to utilize this equation. This was the slope equation we created yesterday. The function of x plus delta x, otherwise meaning the function of where we started plus how much we moved, minus the function of x, or just the function of where we started, divided by delta x, the change in x, the change in how far we moved. So this is kind of an atypical way of looking at the slope equation, but we're going to try it out firsthand today. So here's the deal. We have this function, and we need to find f of x plus delta x and f of x. Now, f of x is pretty straightforward because guess what? This is already f of x. If you recall from the very beginning of our quarantined videos here, we talked about plugging things in to functions. Well, whatever's in these parentheses is what we are plugging in. And if we're just plugging in x, this one already has x plugged in. So whenever we see this in the equation, we can just simply write what we already have here, x squared plus 5. Now the delta x will remain in the denominator as well because there's no function there. There's nothing we got to solve, nothing we got to do. And the only thing that really involves trying something else out is this part, f of x plus delta x. Because we're not just putting x into the function now, we're putting all of this. So here's what we're going to do. F of x plus delta x would actually look like this. Instead of seeing x squared, we would replace it with what is in these parentheses, and we would get x plus delta x squared plus 5. Now what will happen is, if you recall again to what we were doing before, that we had to actually solve or simplify what we have here. We can't just have it left being x plus delta x squared. We actually have to multiply that, where we have to FOIL it. Now this is where it does get a little weird, because we're not just FOILing x plus 5 or x minus 3 or some combination of numbers and variables. We're FOILing two completely independent sets of variable binomials. So here's what's going to happen. We're going to do first x times x. Well, that's x squared. That's straightforward enough. That's not that different than usual. But now we need to do outside. Outside is going to be x times delta x. Now here's what's important. A lot of us would say, well, is it delta x squared, maybe? Well, unfortunately, that's not quite right, because delta x is its own variable. Even though we see an x there, it's different than just x by itself because it represents something else. It means the change in x. So what happens is, just like if we were multiplying a number in a variable or two different variables, we're just going to write those next to each other. You know, if we were multiplying x and y, well, we would just say xy. Or if we multiplied 3 and x, we would say 3x. The same thing happens here. We say x delta x. These two things are multiplying, but they're two separate terms. The same thing happens when we go to the inside part of FOILing. Delta x times x. Again, we get x delta x. Finally, when we move on to the last part of FOILing, we do delta x times delta x, and we get delta x squared. That operates in the exact same way that the first terms did. X times x is x squared. Any variable that you multiply together is going to be that variable squared. So we get delta x squared. We can combine our like terms and put together our two middle sets of variables, x delta x, to ultimately make x squared, and since we have two of these, 2x delta x plus delta x squared. So this is actually going to be what gets written in place of our original squared binomial here. So what we're going to do is we are going to have x squared plus 2x delta x plus delta x squared plus 5 being what we get out of our function whenever we substitute in x plus delta x. So I'm going to go ahead and write that in its place. X squared plus 2x delta x plus delta x squared. And then we have 5, or minus x squared plus 5. Now one thing we want to keep in mind is that we're subtracting this entire quantity, right? We're subtracting x squared and the 5. So what's going to happen there is we're actually going to distribute that negative. That happens anytime we're subtracting an entire quantity or an entire binomial or even an entire polynomial. So in reality, what this looks like is x squared plus 2x delta x plus delta x squared, and instead of minus x squared and plus 5, that negative distributes to be minus x squared minus 5, all over delta x still. Now at this point, we have a whole lot of numbers here, and we can actually combine some terms further. We see we have an x squared and a minus x squared. Well, guess what? Those have the opportunity to just cancel out. In that exact same vein, I totally forgot to write the plus 5 at the end of this from our original function. I'm so sorry about that. But we have a plus 5, we have a minus 5. Those are going to cancel out. That leaves us with merely 2x delta x plus delta x squared over delta x. Now, from what you guys may know about, just math, and whenever we see a whole lot of different things or similarities throughout numerators and denominators, is we see a change in x or a delta x in every single term in this entire fraction. We can actually factor one of those out or cancel out one of those. It's kind of the same idea as if you see every single number in a fraction being divisible by 2, you divide out that 2, you factor out that 2, right? We can do that with delta x. So we cancel out one of these, we cancel out one of these, and we cancel out this one. Now if we cancel all of those out, what we're left with is 2x plus a single delta x over 1. You know, there's nothing left in the denominator there, right? So we've simplified this function, this slope, down as much as possible. And we've actually found the slope of this line to be 2x plus delta x. We don't really have to say over 1 because that's just the same thing as before, right? Now what's really exciting here is that from the beginning we said we were finding the slope of a single point. And if you're finding the slope of a single point, then the change in x, or the change in distance, must be 0. There's no second point to go to. So we have to acknowledge that the value of the change in x is actually 0. So we wouldn't add 0 or anything like that, kind of like what we were talking about or what we saw with the projectile motion stuff. So we just don't even write it as part of the equation if it's 0. So that leaves us with just 2x. Now you may be wondering, why didn't we just consider delta x to be 0 from the beginning? If it's 0, if there's no change, why did we not make that consideration? Well, if we would have considered delta x to be 0 at the beginning, we would have ended up with a denominator of 0 right here. We can't have that. In math, if you have a denominator of 0, then ultimately you have an equation that is undefined, or a number that's undefined. So we couldn't. We had to work this out so that we could cancel out, so that we could remove the delta x's from the problem in order to get just this one left in the numerator. And for us to be able to take the 0, or substitute in the 0 for it at that point, once we no longer are kind of invalidating the equation by making that substitution. So you may be saying, well, if the slope is 2x, how is the slope 2x? Well, it's not that this is exactly the slope, but this is what is called the derivative. This is the derivative of the equation, and this is what allows us to find the slope of any given point. So if I have this line right here, and I said, you know what, I want to find the slope at point 1, or at the point where x is 1, then what I would do is I would substitute in 1 for x in my derivative, 2 times 1, and I would find out the slope at that point is 2. Or if I wanted to go to the point of x is 3, right up in there somewhere, right? X equals 3. Then what I would put in here is I would say, well, x is 3, 2 times 3 is 6, so the slope at the point where x equals 3 is 6. You can keep doing that for any different point on the line. You can try negative 100, you can do negative 1, you can do positive 1,050. Any given point on a line, once you find its derivative, you can just substitute in for x and find the slope of that point. We are going to work tomorrow with graphing those slopes, with talking about other examples. I know this is difficult, but continuing to kind of hammer in the idea of what this is we're doing. But we're really going to get into those other examples tomorrow and see these slopes and talk about, well, how do we know that the point has that slope? What does it mean for the point to have that slope? And we're going to do some graphing tomorrow. So until then, see you later.